Welcome to this video. My name is Mark Sithian. The date today is January 8th, 2025. So the title of this video is DC Electromotive Circuit Design Motor Speed Controller. So this is a motor speed controller lecture on the circuit design. And so first we have to identify the design goal. So the low setting will have a 1500 RPM design goal, the medium setting 4500 RPM, and the high setting 7500 RPM. And that is on just the increments of 100, 200 watts. It's not written in, but 300 watts. So let's say you have a project or a customer or a goal, and they said that the RPMs must be at 1500, 4500, 7500 across 100, 200, and 300 watts of mechanical power output at the shaft. So then you go to work and start on the circuit design and analysis. So the best choice is to have a constant voltage circuit or a parallel circuit. So each one of these circuits, should they have a break in their continuity, this will not affect the other circuit. So that's the advantage of the parallel circuit. And so when a circuit is parallel, it has constant voltage and variable voltage. So if it was series, then it would have constant current and variable voltage. But then if you try to run a break in the circuit for a switch, then you lose the entire circuit. So it's better using a potentiometer or an adjustable resistor for that platform. And of course, these can also be implemented into programmable logic circuits, so you can have a digital version of this. So all you'd have to have is the programmable logic circuit, PLC, and then the information. And then the PLC would do all of the voltage drops, current draws digitally rather than physically with an analog system. But either or, the information is paramount. So we can start by identifying that direct current, the electrical flow is always only from positive to negative. So when you look at a circuit, you always start from the positive current source and you trace the electrical flow as such. So whatever current is drawn at R1 is then leaving remaining current to then travel in series to the next parallel, and on and on. And so then we have a constant projection of voltage across all three circuits. So this is a parallel circuit, which implies constant voltage and variable current. So the first step is to calculate the brake horsepower values at each setting, low, medium, and high. So all we have to do is just take the 100 watts mechanical power at low setting, divide it into 746 watts per horsepower, so we get 0.134 brake horsepower at the low setting, and then we repeat the process, 200 watts at the medium setting, so this is 0.268 brake horsepower, and then 300 watts mechanical power at the high setting, so this is 0.402 brake horsepower. So then we move on to step 2. We calculate the foot-pounds torque at the low, medium, and high settings. So that is based on the brake horsepower equation, 2 pi radians per revolution times the RPM, revolutions per minute, times the foot-pounds torque, then divided into 33,000 foot-pounds per minute, the number of foot-pounds per minute to horsepower, because we're using revolutions per minute, not revolutions per second. So you can use this equation and then solve for the foot-pounds torque component, and then just substitute the known values into the equation. So at the low setting, we have 0.47 foot-pounds of torque. At the medium setting, we have 0.31 foot-pounds of torque. And at the high setting, we have 0.28 foot-pounds of torque. So we'll fill in this data and then convert it to a final print at the end of the lecture here. So step number 3, we have the calculation of motor shaft diameter based on the max power at the mechanical end, so max mechanical power, mechanical wattage, and the max torque output. So that is the 300 watts maximum power, and we know 1 watt is 1 joule per second, and we know 1 joule is 1 Newton meter. So that means 1 watt of power is 1 Newton meters per second. So that is your force component times the radius component to get torque. And so you can just use the highest mechanical power value as 300 newtons times some radius of the motor shaft. So we have to convert the highest torque value, 0.47 foot-pounds of torque, to Newton meters. There's 1.36 Newton meters per foot-pound, so we calculate 0.64 Newton meters. Then is equal to 300R over 1. So we can simplify this to 0.64 times 1 is equal to 300R. And then just it's 0.64 is equal to 300R. And then we solve R. It's 0.64 divided into 300. So we get 0.00213 meters radius. And then 2 times radius is diameter. So then we multiply these out and we calculate 0.004267 meters is the diameter of the shaft to the rating. So we're finding the shaft rating to max torque and max power ratings, so that the torsional flexural modulus is within the specs of the industry standard of metal or material for the shaft. So those can be changed out by just pulling the rotor out after getting the actually it can just slide out with a brushless DC electric motor. So we then convert the diameter in meters to inches, and upon doing so we get 0.168 inches, and we'll size and scale that up to the industry standards. But now we'll move on to solve the components in the electrical circuit here, the DC electrical circuit. So there's 2 equations or formulas we need to use. That's Ohm's law, which says that in a DC circuit the current I multiplied times the resistance R, so amps times ohms, will equate to volts, DC voltage. And then we have DC electrical power in watts, which is simply just the I current times E voltage. So based on the output mechanical power, we can divide that into the efficiency, the electromotive efficiency here. So it becomes the reciprocal relationship when we go from the mechanical backwards to the electrical. Now, if we're going from the electrical to the mechanical, the electric motor is a device to convert electrical power to mechanical power. So we would simply just multiply the electrical power times 0.75 to get the mechanical power output. But because we're going in the reverse direction, we want to know the electrical power required to provide a certain amount of mechanical power based on the electromotive efficiency of the motor. We can then divide into the efficiency. So we get 133.3 watts of electrical power at R1, or the low selector setting. And so we can go and calculate the power, the electrical power at R2 and R3 in the same method. So we get 266.66 watts and 400 watts for R2 medium and R3 high setting. And so then we can take the DC power equation, P is equal to IE, and we can solve for the current component. So algebraically, that becomes power divided by voltage is the current. So now we can solve for the current at resistors 1, 2, and 3. And that's simply just the power calculated at each resistor divided into the constant voltage, 24 volts. So we carry that out in the same method, and we get these current values. And then we move on to Ohm's law, And instead, this time we rearrange Ohm's law to solve for resistance. So voltage divided into current, E over I. So we have constant voltage, and then we just divide the current values at each resistor. And so we can calculate the ohms value at each resistor accordingly. So we can populate these missing blanks in the circuit design. And then the DC current source at the top over here, right here, is the source DC current must be 1.5 times the maximum current draw. So 16.7 amps times 1.5, we should have about 25 amps of current coming in at the source. And so there are three primary sources of DC electrical power, and they are our lithium polymer or ion batteries, an alternator which converts the AC to DC internally through a rotor-stator and diode, and then of course we have just the standard AC to DC conversion, AC power from the outlet converted to DC through a four-way rectifier diode bridge, so just call it rectification. But that should have a 25 amp rating. So if you have a digital controller and you can set the primary power main current, you just enter in 25 on the PLC. And if you want to build this physically an analog system, then you can just get the 25 amp rated positive wire, so whatever gauge that is. So if you're using a lithium polymer ion for this motor, you should have at least 1.1 amp hours or 1100 milliamp hours and a 30C discharge rate and 7 cells, because there's 3.6 volts per cell, so that will give you 25.2 volts DC. So if you check the 1.1 amp hours times 30C discharge, that gives you 33 amps of maximum current. You won't even need that, but that is also within the 1.5 scale of 25. Well, 25 is already 1.5, so you wouldn't have to set the source current controller at maximum 30C. It would be well below that, probably like 22, 24. And so you have a very efficiently running battery. And if it's subject to charging system, then it's going to run really cool. It's not going to work too hard. So that's just a suggestion. So now we'll clean up this and put this in print. And then we can get the industry standard for the shaft diameter. We calculated exactly 0.168 inches, but if we try to turn that into a fraction, we'll get 21 1/25ths is equal to 0.168 inches. But that scales closest to the 3/16 industry standard, 0.1875. So that would fall under an easy to obtain 3/16 inch diameter armature shaft assembly. And so you can quickly put this together. And when the project or your customer or whoever buys this unit, you have the specs that are written, and then they can connect everything and move their switch back and forth, and they have exactly their values of 1500 RPM at 0.47 foot-pounds torque at the low setting, 4500 RPM at the and 0.31 foot-pounds torque at the medium setting, and then 7500 RPM at 0.28 foot-pounds torque at the high setting. And so you notice after the torque and RPM equilibrium is reached, the torque curve, that's when increasing RPM will result in a decrease in torque. So that is true in the real world, and that is true mathematically and graphically. So you see the relationship that, yes, the torque goes up with the RPM from start or rest, but then after it reaches its torque curve equilibrium, then the torque drops and the RPM increases. So it's good to be right at that torque curve. So they may not want to be at the torque curve. They might want to start it and have more torque, and then they might be under a lighter load and want just more motion, so they'll go to the high setting. And then the nominal setting for basically all purpose with medium. So you see 4500 is about where the torque curve would stabilize. So notice we have like a pretty close gesture of torque decrease over a much higher RPM increase from medium to high. So this becomes a functional design. So instead of having to do all this mechanical manipulation on controlling the mechanical power out, you could just build this circuit here and plug it in and have the switch controller go across and changing the mechanical at the flip of a switch at the fingertip. You can get all these values. And there's other ways to put instrumented sensors on this. So you may have another system it's running, maybe another drive, and it has a RPM meter on it. And you can then connect it to another current generating device, maybe like a small alternator. And so it has an efficiency curve on it. So you divide the electrical output into that efficiency. You'll know the mechanical output at the motor as a registry, and then you can have another iteration typed in or programmed in the PLC that reverses it back to the actual electrical power. So you could have a good spreadsheet real time, either through Excel or Python or whatever, or C++, and this becomes a self-contained instrumented sensor. And if it's connected to Android system, then you can control it through Wi-Fi and GPS, internet. So this might be running a system that's determining how much refrigerant goes into a compressor, or it just could be a fan drive that triggers the air conditioner or the heating based on vacuum pressure. And you'd be able to like write this into an app, so it would be in the auto selector, so it would stay at a constant temperature all year round regardless of the heating and cooling. And so you can have just the auto setting, and then it can be locked out and monitored. But it all starts here with building the circuit or writing the PLC and just getting a PLC module and entering all this information in. So very quickly you can control all the physical actions through the electrical field. And remember, energy is conserved. We can't create or destroy energy. So the electrical power is then being converted into mechanical power, and one doesn't have to work too hard or at all. It will be a self-regulating system from the electricity using informatics model to then control the mechanical, because the electrical power becomes mechanical power minus the efficiency losses. So this is a fundamental in DC electromotive circuit design, and in this case the application's motor speed controller. So thank you for watching this video and have a great day.